So, okay, let us, do this very casually. Feel free to interrupt me at any time point. Ask any questions if you want to. Yeah, just don't feel, afraid. Okay, so today I'm going to talk about, well, first of all, I'm very glad to be presenting this at the tutorial. And today I'll be talking about representing longer videos. And so what am I going to talk today? So before we actually, dive into the details, let us try to get an overview of what I will be trying to talk today. So I'll be talking about various attempts by researchers, including myself, on representing longer videos. I will have an opportunity to go through some of the space-time CNNs, I3D, C3D, the things we also mentioned during our panel session. And I'll also have an opportunity to provide you stronger space-time CNN architectures found using neural architecture search. And then we'll move on to the video transformer and have a discussion about what it is exactly doing and why it's actually working and so on. And then finally, I'll talk about TokenLearner, which is one of my very new, recent research. Actually, I'm kind of linking the URL here, but this version of the paper has been pre-released like 2 hours ago, and it will be appearing on arXiv on Monday. So if you are curious about this paper, you can just visit my personal website and check what it is. But in any case, let us dive in. So why are we interested in representing longer videos? Well, in some videos, even a single frame is sufficient to make a decision. However, in some actions, it is insufficient. So I'm giving you 2 examples here from Charay's dataset, I think. They are either taking off the clothing or taking on the clothing. Can you actually tell what they are doing from a single frame? It's unclear. What if I give you more frames, like 16 frames? This is what many state-of-the-art video models are actually handling, 16 frames. Still, it's a bit unclear. What can we do? Well, if we provide more frames, like hundreds of frames, now it becomes quite clear whether this person is taking off the clothing or not. So we do want to represent longer videos, capture the necessary information in such video. How have we been doing this with convolutional neural network? As many people are aware, use of 3D space-time convolution by just treating time as one more axis in the tensor have been quite popular, as well as successful. The idea is to stack multiple 3D space-time convolutions like this. An example is here. This is the slow fast network from Facebook. And if each layer has certain temporal duration, convolutional filter in each layer has certain temporal duration, like 3 frames, by stacking this multiple times, each layer can pass temporal information from nearby frames. So if we stack like 100 layers, we'll be able to capture like 100 and 200 frame information gradually. And many architectures, as I mentioned, were like this. Are there anything else we can do? It might probably be impossible to stack like 300 or 500 layers. So what should we do instead? An easy approach has been just to use temporal pooling. So we apply per frame or per small segment, like 64 frame CNNs over time. And then we try to aggregate them by doing the temporal pooling, and then apply classifier on top of it. This actually worked quite well, handling like even thousands of frames. However, of course, because we are doing the max pooling, we are losing fine-grained information. A slightly better approach will be doing the learning for the pooling. So instead of brute forcefully pooling everything, there were attempts trying to learn to select temporal intervals so that we pool only within certain interval. And then we try to do that by learning multiple time intervals, and then we concatenate the representation. So now the representation will have various temporal aspects of this video. And this has been shown to be at least better than what I am showing you here. And an example of what such time intervals look like if we try to learn them, it actually looks like this. Even in the simple push-up, there is an activity of person going down and there is an action of person going up. So if we are able to segment these two motions differently with different time intervals, we can better represent video compared to, for example, max temporal pooling over the entire sequence. And in complicated action like this, it was able to automatically decompose the entire video into 3 chunks: a person rolling, a person kind of, diving, and a person kind of standing up. And all these were learned without any labels. So this shows some potential. And then later, I further investigated a similar concept by extending it to make the architecture fully convolutional but have the same effect. In this particular thing, I was trying to model everything with convolutional filters. But if we brute forcefully learn convolutional filters, this is the number of parameters you need to learn. You need to learn the value corresponding to each frame. And if your convolutional filter is over like 20 frames, learning 20 values over many channels could be quite a bit. However, if we model the convolution, the filter values of the convolution in terms of the Gaussian mixture, for example, the number of parameters you need to learn are just the Gaussian parameters, mean and variance. And if we have a collection of them, and if we know how to mix them, we are able to have better convolutional filters covering larger interval without learning too many parameters. So people have tried something like this. And based on that, they were able to get reasonably high accuracies. I mean, as you see, red is ground truth, but everything else is response from computer vision systems. And as you're able to see, it's been quite accurate. There were other approaches, like using recurrent neural networks, LSTMs, GRU, sometimes graph neural networks, and peculiarly, there were approaches using formal grammar as well. But I just want to mention them, and I will not go into too much details about what these are. So now, here comes the main story. Transformers, as many of you are aware, have been quite popular recently for image understanding, and in past couple of months, also on video understanding. So let us now have an opportunity to look at 2 different recent research work of mine. One, an effort to make a CNN architecture better so that it captures multimodal, longer temporal information. And you can view this as the last of the previous generation. Still uses CNN architecture, but we want to hack the CNN architecture at its best so that we are able to capture as much information as possible. And then we'll also have an opportunity to look at how transformers now perform better on longer video sequences. So these 2 are the main focuses of my talk today. Okay, so first one, CNN. And this particular model is called AssemblyNet. So what is this about? If you think about a video CNN, as I have mentioned, it either takes an image or a video and then passes it to multiple convolutional layers. Sometimes just one single image is not sufficient, obviously. So we provide multiple images, and this could be as many as like 16 frames or 64 frames, and then doing the striding within, and it can be many things. And it should be 3D space-time convolutional layers. And people also found that sometimes it's quite beneficial to take advantage of other input modalities. Optical flow is not, strictly speaking, a different modality because it's derived from RGB. But people also found that explicitly computing the motion information using optical flow and then treating it as another input modality is beneficial. So in order to build a better video CNN, instead of just having a single stream, many people tried having multiple streams like this. And once, one more thing to mention, and in addition to just treating optical flow as another stream, another input modality, there were also approaches using different frame rate to and treat it as a different modality. And this is particularly important because if we actually think about very low frame rate, like 3 frames per second, This allows you, even if you have like the same 64 frames in this particular network, it allows you to capture longer time interval. So if we actually are able to mix something like this, we'll be able to capture like fine-grained information in smaller interval, as well as coarse information in larger intervals simultaneously, and mix them appropriately and make the best decision out of them. But what's the best way to fuse different modality inputs? It can be fused in many different occasions, setting aside the actual architecture for corresponding to each network. And people try things like late fusion, have two different CNN towers and then fuse them at the end. People try slightly earlier fusion. People also design like design multiple intermediate fusions, which actually work better. So late fusion worked to a certain degree, early fusion worked a bit better, and intermediate fusions worked better. And the main question this particular research work was trying to address is whether this is actually the best or not. And there actually could be many possible connections, not just hand-designed ones, but something like this. And this becomes even more complicated if we have more streams like RGB, low frame rate RGB, motion information, as well as some more semantic object information. And it can be also audio if we want to insert. What should we connect? And how should we connect has been the main questions we were trying to address. And AssemblyNet, motivated by such challenge or the problem, was neural architecture search, CNN. It is a family of evolved neural architecture for video representation. And what we mean by evolved is that we use neural architecture search. And it was focusing on multi-stream connectivity. So you are able to see that there are like 4 different streams connected in like spaghetti fashion. How do we actually obtain that? If you ask me, it also has a form of differentiable architecture search. And what you see, very complicated thing is what we call SuperNet. It tries to connect everything that's possible. We prepare multiple streams, taking different input modality as an input, and then we try to connect everything. And then we try to find the optimal subgraph that maximizes the performance while maintaining the number of parameters. So this is supergraph. We find the subgraph, and then based on the subgraph, we generate the network. And each node within this supergraph actually looks like this. I mean, essentially a ResNet, repetition of residual modules. And in AssemblyNet, it was a mixture of evolution plus differentiable architecture search. So in terms of evolution, it's how things look like. We prepare many randomly connected architectures in the beginning, similar to the RandWire network. And then we try to learn the connection weights. So this actually, what we randomly connect is a network. And when we are training this network, in addition to just learning convolutional filters, we are also able to learn the connection weights. So these are actually weighted inputs. And if the weight is actually near 0, that means that this connection is useless, so we can actually cut it. That's the main idea. And these weights can be trained together with convolutional filters. And that's what we do. So we obtain this, and then we prune unnecessary weights, and then like this. And then we try to mutate it. We sometimes try to add more connections. We sometimes try to split a convolutional node, I mean the ResNet node, and make it 2, and then repeat this evolution multiple times until we get better performing architecture. And AssemblyNet++ was an extension of it. So if I say it now, the main difference between AssemblyNet and AssemblyNet++ is whether we have attention. Attention similar to squeeze and excitation layer, which is channel-wise attention. So this is how AssemblyNet, which I just described, look like. It tries to connect everything, but in AssemblyNet++, it not only tries to connect everything, but it has one more gate before trying to connect everything. And the gate actually is an attention mechanism controlled by something else. So we actually name this peer attention instead of self-attention because the gate is actually controlled by another node. And we actually also need to find which node should be controlling the gating. So this is another connection search, peer attention connection search. So if we visualize self-attention versus peer attention is like this. In self-attention, my gate in connection is controlled by myself. It's just my representation. In peer attention, it's not myself. It could be somebody else. And we actually want to find who is that somebody else using architecture search as well. So long story short, formulated an architecture search, taking multiple different types of input modalities, including different frame rate, so that we can capture longer time interval. And we apply this on Charades dataset. And Charades actually is an interesting dataset because each video in Charades dataset is about like 30 seconds or more. And it's also multi-label dataset because a person does multiple things within these 30 seconds. And we need to label all of them. So, and if we compare, and these blue ones are hand design architectures, and these red one and yellow one are what AssemblyNet tried to do. What AssemblyNet was able to achieve. So by automatically searching for better architecture, it was able to obtain higher accuracy than what humans are designing on such challenging dataset. And we tried this on another dataset, which is Toyota Smart Home dataset. And it also worked well. And just to mention about Charades, if I actually give you a teaser, transformer now, our transformer, new transformer, actually performs even better than this by a significant margin. So let us go there. We'll have an opportunity to look at it. But before jumping to transformer, this architecture search, how much architecture search and the findings from architecture search could benefit was quite significant if you actually see. So these are like base architecture without the newly added attention and object connectivity search. And by adding such information, we were able to see a good amount of increase. And this shows you the potential of what convolutional architectures were able to do. Graduate from previously hand-designed convolutional architecture, CNN architecture, and migrate to automatically design CNN architecture, which actually perform worse than the transformer, which will actually, and will let us talk about it. So now the transformer. Oh, any questions before we jump into the transformer?
One small question.
Yep.
Just regarding the parameter size of the AssemblyNet, of course, the computation, like arriving at it takes a long time, but how large was it compared to the CNNs in the end?
That's a very good question. So if I show you this, you will think that this is way overly complicated and
right.
So many parameters. However, each connection is simply a weight over the connection. So the connection actually doesn't have many weights. It's mostly the number of nodes which dominates the number of parameters. And in terms of the number of nodes, we actually carefully control the channels so that the entire number of parameters become comparable to two-stream CNN. Not one-stream CNN, sorry, but it becomes comparable to two-stream CNN. Yeah.
Perfect. Thanks a lot.
Okay, now moving on to the transformer. So this is, the standard vision transformer. It's so funny to call this standard because it's actually from like 2021, but this is what many people are accepting nowadays. So what do they do? Unlike CNN, which applies convolutional filter to the entire image, what they do first is to split the image into multiple regions. Like in this example, like 9 different regions, and each region is represented as a particular token. And this token is given to the transformer. This is a set operator. So we are actually preparing an image as a set of patches, and then preparing a set of tokens by linear projection. And then transformer magically models a relationship between all these different tokens and then makes the classification, and it did it better than previous convolutional architectures on ImageNet. And if we actually look at what really happens within the transformer, I just mentioned that it magically models all the pairwise relations. And the key here is that the pairwise relationship. So we prepare multiple tokens, and then we try to enumerate through all possible pairings. So For those of you who are familiar with transformer, there is always like query, key, and value. This GIF animation is actually being too fast, but please bear with me. So it has three different things: query, key, and value. And it tries to establish the dot product between every value, every query entry, and every key entry. And what we mean by query and keys are nothing but different projections of tokens. So with transformer, what we are trying to capture is relationship between a particular token and another token, and for all possible pairings. So if I go back to this example, what they are trying to do is they have 9 patches, 9 tokens like this, and within the transformer, they want to model, capture pairwise relationship between all possible pairings within the transformer, which actually looks like this, called multi-head self-attention. And that's how they capture global spatial information. So motivated by that, people tried applying this to videos. This is Vivid, which one of the speakers, Cordelia, talked about in the morning. And if you look at it, transformer always need tokens. And in videos, we also need to generate tokens. How did they do that? Well, similar to Vision Transformer, they splitted frame into multiple patches. And in addition to that, since we can treat a video as tensor with height, width, and time, they also split it temporally. So spatially and temporally split the video to form tokens. And each token is a local space-time segment. Transformer is applied on top of it, capturing the pairwise relations between all these tokens. And again, as mentioned, this is a global representation. Each token has a capability to look at everything else. The actual architecture looks like this. And this actually is identical to the Vision Transformer. What is different is mostly in the tokenization, which is this one. And not only the regular transformer that directly tries to capture space-time relations, they also tried other things like factorizing, encoder, splitting temporal and spatial transformer differently. So instead of doing space-time convolution, you can do, space-time transformer. You can do transformer just with spatial tokens, and you can do the transformer just focusing on temporal tokens. And you can actually mix them like this, doing the spatial and then temporal, and then doing the spatial and then temporal, which actually is what Facebook people also did. Oh, so just to let you know, yeah, this was done by Google recently, about 2 or 3 months ago. This was done by Facebook about 2 or 3 months ago as well. So this is called Timesformer, and they actually took a similar approach. So what we are seeing here is a different tokenization. So similar to Vivid, they tokenized a frame by splitting it into multiple patches, and they did it for every frames. And they tried to find out how to best apply transformer. If we apply just regular spatial transformer, like Vision Transformer, for this particular blue patch, what this is able to look at is the red patches over here. If we do full space-time transformer like Vivid, what this blue patch is able to look at is this entire thing, patches over multiple frames. If we do space plus time transformer, this blue patch is able to look at the red patches here, as well as green patches. And this was also tried in Vivid, but they concluded that this is better than this one. On the other hand, Timesformer concluded that this is better than this. And if you ask me which is better, I'm not really sure. But they are different ways of capturing space-time information by looking at the pairwise relations between tokens. So transformer is all about tokens. If we feed tokens out of space-time volume, it becomes space-time transformer. And why do we actually want to take advantage of transformers? Well, as I have been emphasizing, it's a global video representation. And unlike CNNs, it tries to model the entire space-time structure. It's pretty simple, conceptually, and it's a unified architecture. And people are also starting to claim that it performs better and more efficient. However, okay, why can we just not use such video vision transformer, and be happy with it? There are certain limitations with the such video, space-time transformers, and let me try to point that out and introduce you how we can actually try to overcome it. And the title of this new paper is called TokenLearner: What Can Aid Learn Tokens Do for Images and Videos? Motivation was simple. We simply have too many tokens for videos. If we look at this much input, 64 frames, and if we want to fully take advantage of 64 frames, which is not even too many, that's already this many tokens. That's already this many tokens. Sorry, I messed up. This is the input size, and if we actually tokenize based on the patch size of 16 by 16, this is how many tokens we'll end up typically be having. And if you look at it, this is like tens of thousands of tokens. And we need to model the pairwise relation, so the computation is at least quadratic to tens of thousands. And the previous strategies to overcome such issue of having too many tokens is to use less frame. Vivid uses temporal tokenization and striding. So they actually narrow down, after the tokenization and striding, they actually narrow down the number of time steps to only 4. Times performer, the similar striding or sampling to make the video 224 by 224 by 8, just 8 frames. And there is also some space-time striding that can happen within the transformer models. And our main idea was that, okay, tokenization probably is necessary. Unless we tokenize, we cannot apply transformer. However, why don't we learn to tokenize instead of manually splitting the entire video? This actually has some connection to what Dima mentioned in the previous presentation. If we can learn to focus on important space-time regions and make them tokens we want to consider for the transformer, then maybe there is a chance we can significantly reduce the number of tokens and still perform better. And that is the main motivation of TokenLearner, and that is what TokenLearner is exactly doing. So this is previous tokenization, and this is what TokenLearner is doing, and I'll go into this in a bit more detail pretty soon. So this is TokenLearner. What is it doing? It learns to generate tokens. So these are the tokens I'm generating out of the input tensor. And these tokens actually are generated adaptive to the input using spatial attention mechanism. What do you mean by that? We are trying to weight each pixels differently so that each token can focus on a different subset of pixels. So given input, which could be images or which could be some intermediate tensor, we actually try to learn to generate a spatial mask, selecting which pixels we should use for the tokenization. And then we try to apply that to the tensor itself, and then do some spatial pooling to generate a token. This is one way of generating token. We tried other ways, but this worked the best. So it is a simple learning of the alpha function here, which learns to select, which learns to weight images differently and then aggregate them using weighted summation. It's a simple concept, very straightforward, and we do this multiple times, getting multiple tokens, relying on different spatial subsets. How can we apply this for videos? Well, we just need to repeat such procedure. This is the TokenLearner procedure, multiple times for each frame, and then try to stack them all. That's the simplest approach. So in images, we take height, width, channel as an input, and outputs S times channel. And S here is the number of tokens. And in our case, S, 8 tokens was actually sufficient. So H by W could be like 500, but S actually was 8 per frame. And for videos, as mentioned, we can just repeat this. So we first wanted to validate whether TokenLearner works on images. I mean, this is irrelevant whether we apply this to images or videos. This is a pretty generic formulation. So we wanted to apply this for images first, using the vision transformer as a backbone. How did we do that? We try to insert this somewhere in the middle of the vision transformer. In vision transformer, they have 12 transformer modules, and we inserted in the beginning, at the middle, at the later, and we try to evaluate how it performs. And this is how things look like. This is a particular metric, ImageNet few shot classification accuracy. And this y-axis shows where the TokenLearner is being inserted. This thing, no, means that there is no TokenLearner. 0 means that it is being applied before any transformer. And 0.5 means that it's in the middle of the network. And what you are able to see, here's the performance, and here is the flops, computation amount. What you are able to see is that, yes, if the earlier we apply TokenLearner, the more computation we save. And interestingly, if you actually look at this particular two things, if we actually apply TokenLearner toward the end, it actually performs better than not having TokenLearner, and it actually saves computation as well. And this is actually due to the adaptive nature of our token. Our token is not just a fixed split, it reacts to the input, and I think this is showing its power. And if we actually make the TokenLearner inserted exactly at the middle, we save about half the computation, and we maintain the performance, which is what we used for the other experiments. So this shows ImageNet pre-training, ImageNet fine-tuning. We pre-train with Google in-house dataset, JFT, and then fine-tune with ImageNet. And triangles are vision transformer, baseline, with different channel, different input tokenization configurations. And squares, blue squares are TokenLearner. And as you are able to see, it performs better, for example, like this, than vision transformer while saving computation. And if we actually compare similarly performing models, it saves the computation quite a bit, almost by twice. So it worked on images. And here is more evidence. The blue ones are TokenLearner. Vision transformer. The square ones are TokenLearner. And you are able to clearly see, and x-axis is the computation, y-axis is the accuracy. And you are able to see a clear trend that TokenLearner is doing something. Now we try to apply this for videos. This is a video tutorial, and this is what we are interested in. So as I mentioned, we just try to tokenize each frame differently and then concatenate. And then we gave it to the transformer. More specifically, we are using what is called vector transformer, which actually is quite similar to multi-head attention, except that the number of heads we are using is identical to number of channels. We can actually also replace this to multi-head attention. So yeah, don't pay too much attention to this one. It's transformer. And then after applying transformer, we introduce something called token fuser. So the main, well, not the main problem, but the observation of the TokenLearner is once we tokenize, we have fewer tokens, which is obvious. However, if we have fewer tokens, we cannot really add residual connection. We cannot really go back to the original size, tensor size of height, width, and channel. And in some case, for example, if we want to mix this with convolutional layers, we do want this to be back, not just tokens. So in order to do that, we did token fuser, which is about applying linear layer over space-time tokens and then making them smaller so that we have one representative token per frame. And then we broadcasted such token to the original tensor using residual connection. And then now our input and output has the exact same size while we save the transformer computation with the TokenLearner. And there could be other forms of token fuser. I'm just giving you one example. So now let's apply such thing to videos. Now, unlike images, we have TokenLearner, transformer, and token fuser all together. And this time we follow the Bartlett transformer style, which actually is an extension of ResNet. So unlike vision transformer, Bartlett transformer is doing something like having ResNet modules many times, like 3/3 of the times. And at the last layer, at the last layers, they repeat the module like this multiple times, transformer modules multiple times. And in our case, the input was full 64 frames, no striding or pooling, so we are capturing the full 64 frame aspect of the video. Because for each frame, we only have 8 tokens, nothing more. And this is how things look like on Cherries. It's the same data set we use to evaluate AssemblyNet, and it has many frames. And yeah, the numbers are getting bigger, but if I just try to visualize this, this is how things look like. AssemblyNet was great. It was previously the state of the art. Now, TokenLearner is beating AssemblyNet by like 6% or 7%. And it saves computation as well. I mean, almost by twice, because AssemblyNet was multi-stream, using similar amount of compute as 2-stream. TokenLearner is a single stream. We also applied this on the new Orbit dataset. if you have not heard about it, I mean, it's one of the data sets I very recently, well, not very recently, it's already like December last year at NeurIPS, we released. And this is called anonymized videos from diverse countries. So unlike many of the existing data sets, we try to balance where the geographically, where the data is really coming from. We also try to properly anonymize human face so that we don't get into any trouble. And we also try to respect the license of each video. So each video has Creative Commons license. And yep, it's a static data set as well. And it has like, you know, more than 400,000 videos and more than 800 action classes. And we are able to see that this TokenLearner combined with a backbone is doing a reasonable job. And just to let you know, if we actually use the full transformer, like Vivid, it actually is not that bad. It performs comparably. But once we start looking at the computation, here, flops, this is our TokenLearner. And this is the space-time full transformer, yes, like video vision transformer, Vivid. And you can see the difference. And we did more operations, but I will not go into details. And then I'll just go into the visualization of how the tokens or how the spatial regions the tokens are being generated look like over time. And you can see that initially it was focusing on most of the tokens were actually focusing on the entire scene. But as soon as the person actually enters the building, TokenLearner actually narrows down to something smaller. And when the person actually is doing some activity like interaction with the couch or the bed or the table, I don't know exactly, it also tries to focus on some object-related regions, which is promising. It changes over time. Another example of a person standing up, and you're able to see that initially it's trying to focus on the spatial regions close to humans, and then as the person stands up, it gets larger, and yeah, you're able to see some trend. So to summarize, we want to represent longer videos. We talked about space-time CNNs, including architecture search, and we also talked about transformers. Particular challenge in transformers is we have too many frames, meaning that we may end up having too many tokens. So we are introducing TokenLearner, a simple, efficient, and effective mechanism to reduce the number of tokens so that we can focus on full spatial temporal relationship within the video. And that's pretty much it from me. Just let me know if you have any questions.
Yeah, we have time for like several questions.